You wake up every morning in a universe you do not understand. 85% of all the matter around you is invisible, not hidden behind a star, not tucked away in a black hole, invisible because it refuses to touch light. It holds galaxies together with grip strong enough to bend space itself, but passes through your body like you do not exist. Scientists call it dark matter, and for nearly a century they have been chasing ghosts through billion-dollar machines buried under mountains and strapped to rockets aimed at the cosmos. Every detector comes back empty. Every collision yields nothing. What if the reason dark matter is so strange is because it is not just one thing, but an entire shadow universe running parallel to ours with its own particles and its own physics that we will never directly see. The more we search, the stranger it gets. 1933. Fritz Zwicky at the California Institute of Technology aims his telescope at the Coma Cluster 320 million light years away. He counts galaxies. Hundreds of them whipping around the cluster center at speeds that defy every rule Isaac Newton wrote. The math breaks. These galaxies are moving so fast they should tear themselves apart and scatter into the void. Something invisible with 5 times the mass of everything visible is holding them together. Zwicky calls it dunkle materie, dark matter. His colleagues think he is wrong. The numbers must be off. Galaxies cannot be held together by invisible material, but Zwicky is not wrong. 1970. Vera Rubin at the Carnegie Institution measures something impossible. She points her spectrograph at spiral galaxy Andromeda and tracks the speed of stars as they orbit the galactic center. Basic physics says stars farther from the center should move slower, just like planets in our solar system. Mercury races. Neptune crawls. But Rubin's data shows something else. Stars at the edge of Andromeda move just as fast as stars near the core. The rotation curve stays flat all the way out. The only explanation? An invisible halo of matter surrounds the galaxy, extending far beyond the visible stars. She tests galaxy after galaxy. Same result every time. By 1980, Rubin has proven that dark matter is not just in galaxy clusters. It is everywhere. The evidence keeps piling up. 2006, NASA's Chandra X-ray Observatory captures images of the Bullet Cluster, a collision site 3.7 billion light-years away, where 2 massive galaxy clusters smashed into each other 150 million years earlier. The hot gas plasma, containing most of the normal matter, gets slowed by electromagnetic friction during the collision, forming a bullet-shaped structure in the center. But gravitational lensing maps show the mass is not where the gas is. The mass tracked through bent light from background galaxies sits with the galaxies themselves, which passed through the collision almost untouched. Dark matter and normal matter have been ripped apart by violence. The separation measured by Markovich and colleagues in 2004, then confirmed by Clough and team that same year, shows dark matter does not interact with itself or with normal matter except through gravity. The collision happened at roughly 4,500 kilometers per second. The gas slowed. The dark matter did not. Modified gravity theories that try to explain away dark matter cannot account for this split. The statistical probability of this separation being a measurement error, 1 in 10 to the 15th power, essentially 0. If you value documented astrophysics and particle physics history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual using sources from the Chandra X-ray Observatory press releases, archived at the Harvard-Smithsonian Center for Astrophysics, dated August 21, 2006, and Nature Astronomy Volume 9, published October 24, 2025, by the Leibniz Institute for Astrophysics Potsdam, detailing gamma-ray observations from Fermi LAT that match dark matter annihilation signatures in Milky Way simulations. Now back to the information. What exactly is dark matter made of? Nobody knows. For decades, the leading candidate has been WIMPs, weakly interacting massive particles. Theory says these particles weigh somewhere between 10 and 1,000 times the mass of a proton and interact with normal matter through the weak nuclear force. The math is beautiful. If WIMPs exist with masses around 100 giga-electron volts and interact via the weak force, they would naturally produce the right abundance of dark matter observed in the universe through thermal production in the early cosmos. The self-annihilation cross-section of roughly 3 times 10 to the negative 26 cubic centimeters per second matches perfectly with what we see. This coincidence, called the WIMP miracle, makes them the obvious candidate. So we built machines to find them. The cryogenic dark matter search at the Sudan mine in Minnesota, germanium and silicon crystals cooled to 50 millikelvin waiting for a WIMP to crash into a nucleus and produce a tiny vibration. The Large Underground Xenon experiment, 7 tons of liquid xenon 1 mile underground in South Dakota, watching for the flash of light when a WIMP collides with a xenon atom. The LUX Zeppelin detector that went live in 2025 with sensitivity 50 times greater than LUX, all designed to catch WIMPs streaming through Earth from the dark matter halo surrounding our galaxy. Decades pass. Nothing. Not one confirmed detection. Lux Zeppelin published results in Physical Review Letters on September 30th, 2025, setting the strongest limits yet on WIMP properties, but finding 0 actual particles. The Large Hadron Collider at CERN smashes protons together at energies high enough to create new particles, but produces no WIMPs. Indirect detection experiments like the Fermi Gamma Ray Space Telescope scan for gamma rays from WIMP annihilation in nearby galaxies and dwarf spheroidals, no clear signal. The IceCube Neutrino Observatory buried in Antarctic ice searches for neutrinos from WIMP annihilation in the Sun and Earth. Nothing conclusive. The parameter space, where WIMPs could hide, shrinks with every experiment. Physicist Hugh Lippincott from the University of California, Santa Barbara, said it plainly in October 2025, when the latest LUX Zeppelin results came out. While we always hope to discover a new particle, it is important for particle physics that we are able to set bounds on what dark matter might actually be. The WIMP hypothesis is not dead, but it is wounded. Physicists are looking elsewhere. Enter the alternatives: axions, hypothetical particles lighter than electrons originally proposed in the 1970s to solve a problem in quantum chromodynamics. In a strong magnetic field, axions should spontaneously convert into photons, making them detectable. The axion dark matter experiment led by Leslie Rosenberg at the University of Washington is upgrading its sensitivity to definitively test whether axions exist: sterile neutrinos. A fourth type of neutrino that interacts even more weakly than the 3 known types. If sterile neutrinos have masses between 1 and 100 kiloelectronvolts, they could be dark matter and would decay very slowly, producing X-rays with energy equal to half their mass. Astrophysicist Ezra Bobel from the Harvard-Smithsonian Center for Astrophysics reported in February 2014 a mysterious X-ray signal at 7.1 kiloelectronvolts coming from 73 galaxy clusters, potentially matching sterile neutrino decay. Follow-up observations have been mixed. Some teams see the signal, others do not. Then there's the mirror world hypothesis. July 8, 2025. Physicist Stefano Profumo at the University of California, Santa Cruz publishes a paper in Physical Review Letters proposing that dark matter formed in a hidden sector. A shadow realm with its own particles and forces that obey the same physical laws as our universe but remain completely invisible to us. Think of quantum chromodynamics. Quarks bound together inside protons by gluons via the strong nuclear force. Profumo proposes dark QCD, dark quarks and dark gluons binding together in the hidden sector, creating stable black hole-like objects that account for all observed dark matter. These objects formed in the first moments after the Big Bang and have been drifting through space ever since exerting gravity but nothing else. The theory is testable. If correct, dark matter should clump in specific ways that future observations can measure. Or maybe dark matter is not particles at all but a property of space itself. Another Profumo paper from August 1st, 2025, explores whether dark matter emerged from the universe's own expansion. During a brief, intense phase right after inflation, quantum effects near the rapidly expanding cosmic horizon could have gravitationally generated dark matter particles. No pre-existing particles needed. Just the fabric of space-time, creating matter through quantum radiation at the edge of what was observable in those first fractions of a second. The universe, manufacturing its own dark matter from the energy of expansion itself. Meanwhile, gravitational wave detectors originally built to catch ripples in space-time from colliding black holes are being repurposed to hunt for dark matter. December 15th, 2021. The GEO 600 interferometer in Germany, a laser system with 600-meter arms, publishes results in Nature describing a search for scalar field dark matter. This type of dark matter would behave like invisible waves oscillating coherently across galaxies. As these waves pass through the detector, they would cause the beam splitter and mirrors to vibrate ever so slightly. The detector measured over 1,000 steady signals during 7 days of observation across 3 years, but concluded all were noise from vibrations and electronics. A real dark matter signal would produce a rock-steady hum at a single frequency determined by the particle's mass. GEO 600 saw nothing, but the technique works. Gravitational wave detectors have sensitivity at or beyond quantum limits, making them capable of detecting dark matter if it exists as a scalar field. The search continues. January 9th, 2025. Researchers at Nanyang Technological University in Singapore publish in Science a breakthrough technique using photonic crystals that could detect actions by showing that photons can mimic axion behavior in 3 dimensions. Previous experiments only worked in 2 dimensions. This matters because axions, if they exist, move through all 3 dimensions of space. The crystalline structures developed by the Singapore team, published under DOI 10.1126/Science Point ADR 5234, are expected, according to co-author Yanis Simrtsidis from the Center for Axion and Precision Physics Research in South Korea, to become a practical tool for searching axion dark matter in the near future. How much dark matter is out there? Measurements from the Planck satellite mapping the cosmic microwave background give precise numbers. The universe is 68.5% dark energy, 26.7% dark matter, and only 5% normal matter. Everything you can see, touch, or measure makes up less than 5% of reality. Dark matter is 85% of all matter. These numbers come from analyzing tiny temperature fluctuations in the cosmic microwave background radiation left over from 380,000 years after the Big Bang. The exact pattern of these ripples tells us how much normal matter, which interacts with photons, and dark matter, which does not, were present in the early universe. Independent measurements from galaxy cluster counts and gravitational lensing maps confirm the same proportions. Mohammed Abdullah from the National Research Institute of Astronomy and Geophysics in Egypt and Chiba University in Japan used a technique called mass richness relation, published in the Astrophysical Journal in September 2023. His team compared observed galaxy clusters to predictions based on dark matter models and calculated 31.5% total matter, 68.5% dark energy. The numbers match. Dark matter dominated the universe for most of its history. In the early cosmos, when everything was packed tighter, dark matter's gravity was stronger. But dark energy, a mysterious force causing the universe's expansion to accelerate, has stayed constant. As space expands, more space comes into existence, and with it, more dark energy. Right now is the only moment in the entire 13.8 billion year timeline when the influence of dark matter and dark energy are roughly equal. Going forward, dark energy will increasingly dominate. The universe will expand faster and faster. Dark matter will become relatively less important, but for most of cosmic history, dark matter held everything together. Without dark matter, galaxies would not exist. Computer simulations show this clearly. In the first few 100 million years after the Big Bang, dark matter formed dense clumps through gravity. These clumps pulled in hydrogen and helium gas. The gas collapsed and ignited, forming the first stars. The stars gathered into galaxies. The galaxies gathered into clusters. Remove dark matter from the simulations and none of this happens. The gas remains too diffuse, gravity too weak. The universe stays dark and empty. Dark matter is not just holding galaxies together now, it built them in the first place. November 5th, 2025. A paper in Physical Review Letters by Moritz Muru and colleagues from the Leibniz Institute for Astrophysics, Potsdam and Hebrew University of Jerusalem reveals something unexpected about dark matter in our own galaxy. They used the Hestia simulation suite to model the Milky Way's formation, including all the violent collisions with smaller galaxies over billions of years. These crashes did not just build the Milky Way, they reshaped its dark matter core. The simulation shows dark matter near the galactic center arranged in a distorted non-spherical distribution. This specific configuration closely matches the mysterious gamma-ray glow detected by NASA's Fermi Gamma Ray Space Telescope coming from the Milky Way's heart. For over a decade, astronomers have wrestled with this galactic center excess. The simplest explanation? Dark matter particles colliding and annihilating, producing bursts of gamma radiation. But the pattern did not quite match what you would expect from a smooth dark matter distribution. The new simulations solve this. Past collisions warped the dark matter into exactly the shape needed to produce the observed gamma rays. Dark matter is back as a strong candidate for explaining our galaxy's glowing core. October 23, 2025. Researchers at the University of York publish in Physics Letters B a proposal that challenges the assumption that dark matter is completely invisible. According to the paper by A. Akar and colleagues, dark matter might subtly color light red or blue as photons pass through regions filled with it. The effect would be tiny but detectable with future telescopes. The idea uses a network-like model of particle connections. Light does not interact directly with dark matter, but could be influenced indirectly through intermediary particles. If correct telescopes, scanning distant galaxies, could pick up these faint color shifts revealing where dark matter concentrations exist. The finding could revolutionize the search by giving dark matter an optical signature, however faint. What about primordial black holes? Another dark matter candidate. These are not the black holes formed from dying stars, but tiny black holes that might have formed in the chaotic first second after the Big Bang, when density fluctuations were extreme. If primordial black holes exist with masses between 10 to the negative 5 and 10 solar masses, they could be dark matter. They would gravitationally lens background starlight. Astronomers have searched extensively using microlensing surveys. Results published in September 2024 by the Tata Institute of Fundamental Research in the Astrophysical Journal Letters show that gravitational wave observations from LIGO and Virgo constrain how much dark matter could be primordial black holes. If they make up a significant fraction of dark matter, we should see lensing effects and gravitational wave signals from merging black holes. So far, nothing conclusive. Other observations, like cosmic microwave background data, tell us primordial black holes heavier than the Sun can only contribute a very small fraction of dark matter. They have not been ruled out entirely, but the window where they could be dominant is shrinking. If you value deep research like this, subscribe, comment your city. This information comes from peer-reviewed sources including Nature, Volume 606, published December 15, 2021 for GEO 600 scalar field dark matter searches, and Science Volume 393, published January 9, 2025. DOI 10.1126/SciencePoint-ADR 5234 for photonic axion insulator techniques, developed at Nanyang Technological University. Now back to the information. There is a particle physics problem called the hierarchy problem. Why is the Higgs boson mass 125 giga-electron volts when quantum corrections should push it to the Planck scale 10 to the 19th giga-electron volts? Supersymmetry solves this by proposing every particle has a heavier superpartner. The lightest supersymmetric particle would be stable and a perfect dark matter candidate. This is another reason physicists loved WIMPs. They fit naturally into supersymmetric theories. But the Large Hadron Collider has found zero evidence for supersymmetry, despite smashing protons at energies up to 13 tera-electron volts. No superpartners detected. The parameter space for supersymmetric WIMPs is shrinking. Not eliminated, just shrinking. Then there is the small-scale crisis. Dark matter simulations. Predict galaxies should have dense cusps of dark matter at their centers. Observations show flat cores instead. Simulations predict lots of small satellite galaxies orbiting larger galaxies. We see fewer satellites than predicted. These discrepancies happen at scales smaller than galaxies. Maybe the simulations need better resolution. Maybe baryonic physics like supernova feedback changes the dark matter distribution. Or maybe the dark matter model is wrong at small scales. Some researchers propose self-interacting dark matter. Standard cold dark matter is collisionless. Particles pass through each other without interacting. But if dark matter particles occasionally scatter off each other through a new force, it could smooth out the dense cusps and reduce satellite counts. Observations of colliding galaxy clusters like the Bullet cluster allow good limits on how much self-interaction is allowed. Too much, and dark matter would behave like the gas slowing down during collisions. It does not. So if self-interaction exists, it must be weak. Weak enough to be consistent with the Bullet cluster, but strong enough to solve small-scale problems. This is a narrow window. Another idea: warm dark matter. Particles moving faster than cold dark matter when the universe was young. This would prevent the smallest structures from forming, explaining why we see fewer dwarf galaxies than predicted. Sterile neutrinos with masses above 30 kilo-electron volts could be warm dark matter. But observations of the Lyman alpha forest gas clouds between us and distant quasars constrain how warm dark matter can be. The gas distribution depends on the matter power spectrum. Warm dark matter with masses below a few kilo-electron volts is ruled out. Warmer is not dead, but like WIMPs, the allowed range keeps shrinking. What about fuzzy dark matter? Ultralight particles with masses around 10 to the negative 22 electron volts. These particles would have wavelengths measured in kiloparsecs. They would not behave like individual particles, but like a coherent quantum wave filling galaxies. This could naturally produce flat cores instead of cusps, because quantum mechanics prevents the wave from collapsing into a sharp point. Fuzzy dark matter also predicts a specific pattern in the distribution of satellite galaxies. Observations of dwarf galaxies around the Milky Way and Andromeda are beginning to test this. So far, the data is inconclusive. Fuzzy dark matter remains viable. November 4th, 2025. Research published in Nature Astronomy by Hyunbai Park and colleagues from Tel Aviv University proposes using radio waves from the early universe to detect dark matter. In the cosmic dark ages, 100 million years after the Big Bang, before the first stars formed hydrogen gas-filled space, Dark matter clumps pulled this gas together, making it denser. Dense hydrogen emits stronger radio waves at a specific 21 centimeter wavelength. The cumulative effect of all these hydrogen clouds across the early universe should produce a detectable radio signal. The size and distribution of dark matter clumps depends on dark matter's properties. Measure the radio signal and you'll learn about dark matter. The catch? Earth is too noisy. Radio interference from satellites and ground sources drowns the signal. The solution? Put a radio telescope on the far side of the moon. The moon itself would block Earth's radio noise, creating a perfectly quiet environment to listen for dark matter's fingerprint in the primordial hydrogen signal. The paper published October 24, 2025 in Nature Astronomy under DOI 10.1038/S 415-50-0250-26370 shows simulations predicting what the signal should look like. Missions are being planned. Gravitational lensing provides another way to map dark matter directly. When light from a distant galaxy passes near a massive object, the object's gravity bends the light, creating distorted images. Strong lensing produces multiple images, or Einstein rings. Weak lensing creates subtle shape distortions in background galaxies. By measuring how much light bends, you calculate how much mass is doing the bending. The Dark Energy Survey used this technique, mapping 26 million galaxies, to create a dark matter map covering 1/30th of the sky. Published August 2017 by Fermilab, the map shows dark matter concentrated in filaments and nodes exactly as simulations predict. Red regions have more dark matter, blue regions less. The large-scale structure matches predictions from the Lambda cold dark matter model. Dark matter clumped together over billions of years, building the cosmic web on which galaxies hang like dew on a spider's web. What would happen if dark matter does not exist? Modified Newtonian dynamics, or Mo1D, proposes that gravity behaves differently at very low accelerations. Below a critical threshold, roughly 10 to the negative 10 meters per second, squared gravity becomes stronger than Newton predicts. This could explain galaxy rotation curves without dark matter. Stars at the edge of galaxies experience such low accelerations that MOND's modified gravity kicks in, keeping them moving fast. MOND fits rotation curves for many spiral galaxies remarkably well, but MOND struggles with galaxy clusters. It cannot explain the bullet cluster. It cannot explain gravitational lensing observations without adding some invisible mass. It does not predict the cosmic microwave background patterns. MOND works at galaxy scales, but fails at larger scales. That is why most cosmologists stick with dark matter. One explanation that works everywhere versus a modified gravity theory that only works sometimes. There are other modified gravity theories. Scalar tensor vector gravity, or TVES. Massive gravity. Many-body gravity. Each tries to explain observations without dark matter. None have been as successful as Lambda cold dark matter at explaining everything from rotation curves to cluster collisions to cosmic microwave background to large-scale structure. The simplest explanation that accounts for all observations is dark matter exists. We just have not detected the particles yet. Here is the core strangeness. Dark matter is everywhere. You're swimming in it right now. The Milky Way's dark matter halo extends far beyond the visible galaxy, containing roughly 1 trillion solar masses. Earth orbits through this halo at 220 kilometers per second. Billions of dark matter particles pass through your body every second. You feel nothing. They interact so weakly that the entire planet Earth is essentially transparent to them. Only gravity connects dark matter to our world. That is why detection is so hard. You cannot build a wall to stop something that passes through all walls. You can only wait and hope for the 1 in a billion chance that a dark matter particle happens to hit a nucleus in your detector hard enough to register. The direct detection experiments account for this. They use tons of material. The LUX Zeppelin detector holds 7 tons of liquid xenon. The larger the detector, the more target nuclei, the more chances for a rare collision. They bury detectors deep underground to shield from cosmic rays. The Sudan mine in Minnesota, the Sanford Underground Research Facility in South Dakota, the Gran Sasso Laboratory in Italy. Miles of rock filter out almost everything except dark matter and neutrinos. They cool everything to near absolute zero to reduce thermal noise. They build with ultra-pure materials to eliminate radioactive contamination. Every precaution taken, still nothing. October 31st, 2025. An article on phys.org describes the mass range dark matter particles could occupy. On the heavy end, a single particle might weigh 10 to the 24 to 10 to the 30 electron volts. That is somewhere between the mass of a bacterium and a small insect. Any heavier, and we would have seen them through gravitational lensing by now. On the light end, particles could go down to 10 to the negative 21 electron volts. That is where fuzzy dark matter lives. Between these extremes, spanning 50 orders of magnitude, lies every possible dark matter candidate. WIMPs sit around 10 to the 11 electron volts, axions around 10 to the negative 5 electron volts, sterile neutrinos around 10 to the 4 electron volts. We are searching across an absurdly vast range of masses. No wonder we have not found it yet. What if dark matter clumps into structures? Not individual particles, but bound states. Dark atoms, dark molecules, dark stars. If the hidden sector has its own dark electromagnetism, dark matter could form complex structures invisible to us, but gravitationally significant. Some theories propose dark matter forms halos around rotating black holes. These halos would gradually extract angular momentum from the black hole through a process called superradiance. As the dark matter accumulates, it could reach densities high enough for particle collisions to occur, producing gravitational waves. Researchers, including Lily Sun from the Australian National University, published work in July 2022 showing that future gravitational wave detectors like DeSigo and BBO could detect these signals, revealing dark matter through its interaction with black holes. The signals would be continuous waves at specific frequencies, determined by the black hole's spin and the dark matter particle mass. Decades-long observations needed, but potentially definitive proof. The Laser Interferometer Space. Antenna, or LISA, launching around 2037, will search for gravitational waves from supermassive black hole mergers in distant galaxies. A side benefit? LISA could detect dark matter signals. October 22, 2018, researchers from the University of Zurich published in the Astrophysical Journal showing simulations of dwarf galaxy formation reveal a strong link between black hole merger rates and dark matter concentration. More dark matter means more frequent black hole mergers. By measuring gravitational waves from merging black holes in dwarf galaxies, LISA could constrain dark matter properties. The connection between black holes and dark matter can now be described mathematically. Gravitational wave astronomy is opening new windows into the dark universe. Meanwhile, theorists keep proposing new candidates, gravitinos, the supersymmetric partner of the graviton, dark photons, hidden sector versions of photons that kinetically mix with ordinary photons, QCD axions specifically tied to the strong force, axion-like particles that mimic axion properties without solving the original quantum chromodynamics problem, primordial black holes with masses below 1 solar mass, asymmetric dark matter, where dark matter and dark antimatter annihilated in the early universe, leaving only dark matter behind, similar to the baryon asymmetry that left us with more matter than antimatter. Each candidate makes different predictions. Each requires different detection strategies. The dark matter problem is not one problem. It is dozens. Some researchers question whether dark matter is matter at all. Could it be a modification of general relativity? Einstein's theory works perfectly at solar system scales. Binary pulsars confirm it to extreme precision. But maybe at galactic scales, where accelerations are tiny or curvature is spread over vast distances, general relativity needs corrections. Emergent gravity theories propose that gravity is not fundamental but emerges from quantum entanglement of space-time itself. In this view, dark matter effects are really thermodynamic consequences of how information is stored on cosmic horizons. Eric Verlinde at the University of Amsterdam has developed this idea. It explains galaxy rotation curves and some aspects of large-scale structure, but like Mund, it struggles with cluster collisions and cosmic microwave background. The framework is still being developed. Most physicists remain skeptical. Then there's the no dark matter option. March 16, 2024. Rajendra Gupta from the University of Ottawa published work suggesting the universe might not need dark matter at all. Using a combination of covariant coupling constants and tired light theory, Gupta proposes that forces of nature decrease over cosmic time and light loses energy, traveling long distances. This model fits observations of galaxy distributions and cosmic microwave background evolution. In this framework, the universe is 26.7 billion years old, not 13.8 billion. Dark energy is really the weakening of fundamental forces as the universe expands. Dark matter is unnecessary. The model is controversial. Most cosmologists point to evidence that forces do not vary significantly over time. But Gupta argues his model, being consistent with key observations, deserves consideration. Here is what we know for certain. Something with mass we cannot see is holding the universe together. That something does not emit, absorb, or scatter light across any wavelength. It interacts only through gravity. It makes up 85% of all matter. It clumped together in the early universe, seeding galaxy formation. It forms halos around galaxies extending far beyond visible edges. It passes through itself in normal matter without interacting except gravitationally. It has shaped every large-scale structure we observe. And despite nearly a century of searching, we have never directly detected a single particle of it. The hunt continues across dozens of experiments worldwide: liquid xenon detectors, cryogenic crystal detectors, magnetic axion detectors, X-ray telescopes searching for sterile neutrino decay, gravitational wave interferometers repurposed for scalar fields, radio telescopes planning lunar missions, colliders smashing particles at record energies. Each experiment probes a different corner of parameter space. Each failure narrows the possibilities. Each year we learn more about what dark matter is not. Some results published October 18, 2025 in Physical Review Letters by Alexandra Gödel and colleagues describe new LEGO searches for scalar field dark matter examining data at 10 Hz, finding no signal. This places the strongest limits yet on scalar field dark matter with a mass of 10 to the negative 13 electron volts per c squared. The sensitivity of gravitational wave detectors to dark matter improves with each observing run. The third-generation detectors like Einstein Telescope and Cosmic Explorer coming online in the 2030s will push sensitivity even further. The charged gravitino hypothesis emerged September 25, 2025. Physicists propose ultra-heavy stable particles from supergravity theory. Unlike axions or WIMPs, these carry electric charge. Charged dark matter would interact differently with ordinary matter. Detection would require new techniques. Colliders could produce them directly. The mass estimates put charged gravitinos far above current collider energies, but future machines might reach them. July 13, 2025. Researchers published in the monthly notices of the Royal Astronomical Society proposing dark stars. These are not normal stars powered by fusion, but hypothetical objects powered by dark matter annihilation. If dark matter particles accumulated at the centers of the first stars, their annihilation could release enough energy to make the stars glow. Dark stars would be larger, cooler, and longer-lived than fusion stars. The James Webb Space Telescope found extremely bright galaxies in the early universe that conventional models struggle to explain. Could some be dark stars? Spectroscopic observations could tell by looking for unusual chemical signatures. We live in the strangest possible universe, one where the stuff that makes stars, planets, and people is a tiny minority. Most of reality is inaccessible to direct observation. Dark matter shaped the universe we see, but remains stubbornly hidden. Every new observation, every new experiment brings us closer to understanding, or reveals how much stranger the situation is than we imagined. The LUX Zeppelin detector operating in October 2025 did not find WIMPs, but ruled out vast regions of parameter space. This is progress. Negative results matter. They tell us where not to look. They guide the next generation of experiments. In 2004, a mass grave in Scandinavia. No, not that kind. November 5th, 2025. The Hestia simulation revealed something unexpected. When the researchers from Leibniz Institute for Astrophysics Potsdam ran high-resolution simulations of Milky Way formation, including every recorded collision with dwarf galaxies over 10 billion years, they found dark matter does not settle into a smooth spherical halo. Past violence left scars. The crashes warped dark matter into asymmetric structures. These distortions match the gamma-ray excess from Fermi-Lat observations exactly. The simulation shows dark matter density peaks offset from the galactic center aligning with observed emission. For 15 years, scientists debated whether millisecond pulsars or dark matter cause the gamma-ray glow. The new work tips the scale back toward dark matter. The signature is not from individual annihilations scattered randomly, but from the specific distribution created by our galaxy's turbulent history. Dark matter carries memory of ancient collisions frozen in its spatial arrangement. That reframing changes everything. We thought dark matter would be simple. Smooth halos, spherical distributions, clean predictions. Reality is messier. Galaxies grow through violence. Every merger reshapes the dark matter. The universe is not a physics problem solved with elegant equations. It is a crime scene. We are detectives trying to reconstruct what happened using fragmentary evidence. The dark matter is still there surrounding us, but its configuration tells a story of impacts and chaos stretching back to when the universe was young. We do not know what dark matter is. We know what it does. It bends light. It holds galaxies together. It structured the cosmos. It dominates the mass budget of reality, and every attempt to catch it directly has failed. That is the strangeness. Not that invisible matter exists, but that nature has constructed a substance so thoroughly disconnected from the electromagnetic force that it might as well inhabit a parallel universe. We share space with an entire shadow sector of reality, and can only perceive it through the way it warps space-time. That is not just strange. That is reality operating on principles we barely comprehend. The universe is far weirder than we imagined. Dark matter proves it.